trying to remember how many years there's been IWACOs. We don't run them every year, but anyway, if you do borrowing on the conference, this is what you get. I just realized, and there is that Al Pacino playing Shylock, famously in Shakespeare's play about the bad things about borrowing. But in spite of that, and I did notice I haven't really had a chance to look at the other papers yet. There's at least one paper on a borrowing calculus and another one from borrowing from SEP logic, all these sort of things. What am I talking about in about 30 minutes or so? I'm going to start by talking about the wood from the trees, which is an English phrase. I believe the American phrase is the forest from the trees. Hopefully I'm going to talk a bit about borrowing versus ownership and maybe where we can go with Rust or with other languages. So here's currently my favorite short Rust program. And the question is, what's the lifetime of that borrow? In another life, when I had a teaching job, I actually gave this as an example in the class, just, I don't know, because I'm perverse. But that Rust I can give it away. Rust will actually accept this. What's the lifetime of that borrow? Because that there, x is a mutable variable that is a borrow of, as Rust would say, a borrow of the box of I size. Yes? It has two lifetimes, yes. I was very nearly going to say, you could even argue it has two lifetimes and then a non-lifetime. So I was going to say, you've all got the answer right because nobody's answered because there isn't actually an answer to the question. What's going on here? Now, does it compile? The answer is yes. What actually kind of happens is it's almost as if the declaration was moved for all effective purposes, was duplicated and then moved inside each of the curly brace blocks that we can see here. Okay, so in that sense, you're quite right. There's one lifetime here. There's another lifetime here. And when I say there's a non-lifetime, is if you try to do anything, well, unless you put in extra code to assign to X, at which point it would get a third lifetime. There's not really any lifetime for X within here or within here. If there are any ox-camel people in the room, please tell me your language won't accept this. Because I've had to explain to somewhat, motivated final year students about why you might want a language and why you might want to do this, and we just all kind of want to curl up in the corner and cry. And I guess underlying this talk is that how we think about programs and how we think about what we tell people about programs is important or possibly more important than the details of the thing. Should this compile? Well, personally, I think no, but I think a more interesting or an important question is why? How do we know what basis would we have for making arguments as to why our language design should support this or shouldn't support this? So, there we go. First takeaway, I don't know if this is the first takeaway, this is a wood. Whoops, sorry, oh God, now I'm going backwards. No, I'm not. Right, this is a wood. Any idea which wood it is? I'm from New Zealand. You've all seen Lord of the Rings. If you fly to New Zealand, because it takes 10 hours or 12 hours to get there from here, there's, I believe, a law that says Lord of the Rings has to be installed on all the seatback entertainment systems, and you're required to watch them if you haven't already when you fill in the quiz on your arrival card. Okay, that's a joke. But anyway, this is a wood in New Zealand, and it's called a goblin wood. And, it's got all these kind of cool trees. I think that one looks like an ent. The actual wood sequences, if there are fans of the Lord of the Rings films here, it was our economy for a number of years. Excellent. We need your continued investment in merchandise to keep our country afloat. This is why I don't have a job anymore. No, but although this is what New Zealand woods actually look like, the actual woods in the film was shot in a leaky warehouse next door to Wellington, well, not quite next door to Wellington Airport, but not very far away. And it was all a stage set. That's the wood, and it's a pretty cool wood. Or rather, that's the trees in the wood. Because the wood is pretty cool, But here's what it looks like to NASA. That wood is literally a wood called goblin wood. It's in New Zealand. It's in a province called Taranaki, I guess, and that is Mount Taranaki there, seen directly from the top. There's obviously snow on it, and there is the wood, or the forest, and it's a circle. And that's kind of important. And in fact, if you're a fan of Lord of the Rings or The Hobbit, you'll know there's actually quite a lot of time when the characters do wander around a wood and get stuck going round and round in circles. And they're not doing algorithms to try and work out whether a linked list is circular. Okay, I can't believe I said that, but anyway. Being able to see the trees is important, but you need to think about the wood. This is sufficiently striking that various people have said, why is it? Is this some weird natural function? Is this due to the, the biology of the trees? And of course, my answer, because if you ask me on a good day, well, in fact, it doesn't matter whether it's a good day or a bad day. If you ask me a question, I will say the answer is always object ownership. But in this case, it is, because that wood, the goblin wood, is part of a national park. And the national park is kind of co-owned, and whereas all the land around it, that's just standard New Zealand farmland. You can't actually see the cows and the sheep, but that's basically what there will be there. But that wood that is a national park, it's actually owned technically by the mountain, which recently was granted legal personhood. And before you start yelling at me, I'll point out that giving a mountain legal personhood is no worse than giving, I don't know, Microsoft legal personhood. And we're quite happy to do this to corporations, so we may as well do it. There's a mountain, there are a couple of rivers in New Zealand that have legal personhood. Hell, the ACM has legal, for all I know, Splash has separate legal personhood from the ACM in Singapore. I don't know if you had to set up some kind of company so that if it all fell apart, the university wouldn't get sued. But anyway, ownership, that's what gives that the shape. And there is this saying, again, that's actually the Americans. I actually have a song which quotes those lyrics, but apparently I didn't realize the UK version would be not see the wood for the trees, which this kind of has a second meaning, because wood can either mean the actual, bits of wood, or it can mean a wood. And the American version, the forest for the trees. We should think about the large-scale structures at least as well as the smaller-scale ones. And if you're going to explain why that goblin wood is there, being able to say things like, well, it's actually a national park. It's a national park that's now co-owned by the Tangata Whenua, the indigenous people. That's why it's this circle, and if you want to go to it, all those things are kind of important to know, as well as the fact that it'll kind of look cool, and you're going to have to thread your way. I didn't get any pictures of the sort of twisty little paths all alike that you would have to find your way through. So, what's that got to do with this? Well, I have a tradition of being somewhat mean to people, but actually, I only put up work from people I only put up work that I like. For example, there's this lovely paper by Will and Gavin and Sriram, which talks about presenting a conceptual model for how ownership should work in Rust. Well, that sounds good. That's sort of what I'm kind of into. Conceptual models and these kind of things are borrow checking, flow-sensitive permissions, paths into memory. Great. And, they've got some really nice stuff. Those guys have obviously got a great infrastructure in Racket, which they're, is that right? I guess that is actually Rust code, but probably building on that, I don't know. This is much better than things that I remember from 10 years ago, like it was called the Interactive Python Tutor or something. And, it shows you there is the stack and there is the heap. But most of the work in that paper, and I think there's a formalization, is a model which has, well, capabilities, which, as Martin reminds us, goes back to Dennis and Van Horn in 1966, before even I was born. Although checking their paper, they would actually call these various things, can you read, can you write, do you have ownership, whatever. They actually called those things access indexes or something weird. And the capability is, well, it's a pointer plus all the things that you can do, the effects you can cause through that pointer. So a pointer with read and a pointer with write are two separate capabilities. They may be a capability in some sense to the same underlying state. They may be a capability where doing something on one thing affects something else, but they're basically two separate capabilities with different, well, Unix calls them permissions. I blame some guys that wrote a paper, God, more than 20 years ago, that kind of publicized the use of the word capabilities for those kind of things, and I sort of wish that we'd picked a different word. But anyway, most of the time if I talk capabilities, I will have the capability in the sort of object, a wider capability sense, the same that it was used in capability computers as meaning the unification of an address and the rights that you may have over it. And maybe one or two other things we'll throw in. So there's that. These are diagrams, but I'm going to say these are fine, but they're still about the trees. They're not about they're not even about the trees. They're about the wood. Sorry, they're about the trees, not the big thing. Knowing that, this will tell you, okay, you don't have appropriate permission to do something, and that's important to know, and it's important to know if you're writing programs, and it's important to understand, in the same way at some level that it's important to understand where, I don't know, the way the bits go, when you add two complement numbers together. Every programmer should understand that. But it seems to me these arguments are operating at that level. Tree borrows, once again, another nice paper that was in PLDI, and they say, well, it's about keeping track of aliases. So here, this is all within one scope, and we can see we make a mutable variable, and we take these, well, I shouldn't have said, well, actually they said aliases, because I ripped this out of a paper, which is a bad habit I've got, but at least I don't misquote things. So they say keeping track of aliases, but the Rust term for that is borrows. And so these things here are all mutable borrows of a mutable Rust variable. And they do a tree here, which is, well, that's the structure of sort of the way these aliases get established, yeah? And then they have this great FSM, which I really think Ralph should put on a T-shirt, which is, it's effectively the way the compiler or the programmer needs to think about the state of various references and things in Rust programs when they go through. I'm sorry, I'm going to have to speed up a bit, so apologies to Alex, because I was going to say a similar thing about place capability graphs, which is another nice paper. And look, it's got these diagrams. I like pictures. I think, at least half the time, I kind of think in pictures. And once again, these pictures are about the way to borrow flows. And this one is particularly cool, and I really like, we really seem to be approaching on Feynman diagrams there. I don't know if, in fact, somehow we are creating, I don't know, an object-anti-object pair in the garbage collector that sort of annihilate and... Actually, that's not a bad idea. Someone remember that for later. Okay, right. That was supposed to take... Oh, it has only taken... Oh, it's supposed to take shorter than that was. Anyway, if these things are looking at the individual participants in our forest, the individual trees, when we take a step back, what is ownership? Well, apparently, according to, again, the Rust book, by ripping pages out of things, I don't have to type the slides myself. I presume most people are familiar with this, yeah, more or less, or no, you're lucky. Sorry, I shouldn't say. You can kind of think of it as C++ with, well, more C++ than C++. Right. There are these ownership rules. Each value has it says each value has a variable that's called its owner, which I would probably disagree with. The important use there is the word value, not because I think necessarily they do things with values, but that's the way they think about it. And by value, they almost mean a chunk of memory. In other words, it's value not used in the sense you might use, well, in Haskell, but it's a value in the sense that, once again, you might use in C++, or to step back, C, or to step back even further, BCPL. It's a chunk of memory. And then the other bit that people talk about is this borrow checker, where we say, okay, this is where, you've got a reference here, and the question is, what are these references allowed to be? And trying to explain that is what a lot of these capability models are all about, saying what is allowed to be referenced, what is not, what are you allowed to do given a particular reference, and they're all very detailed and they're all very low level. And then it introduces this idea of lifetimes. No time travel is one way to put it, and or in Rust speak, the target lifetime must enclose the source lifetime. Okay? And they also say no time travel, which means, I guess, most of the time, blah, blah, blah. Again, it's basically similar. You can't go back in time, but I'm afraid I have to ask you all to come back in time. To, in fact, 1998, where a very clever chap called James Clark and David Clark and some Australians, well, one of them was a New Zealander, but enjoyed drinking, put this thing into Uppsala, And it's based on another paper which is possibly more readable for normal people called Flexible Alias Protection in ECUBA that year. And it said, look, if we want to keep all the promises that object orientation makes, particularly things about abstraction, about being able to think of an object only as an interface, and which protects its own implementation, so we can swap that or change it or rely on this encapsulation for security, then we need to make sure that some rules are obeyed. No incoming references is the big one. So you can't get into the inside of an object without going through the object that represents that object. And you can't get to the object representing an object unless you have actually gone through the object which is representing the whole, the higher level of abstraction. Hopefully that makes sense. There will be arguments with a little less hand-waving shortly. Another way to think about it is that target object's owner must, if you've got a reference from a source to a target, the target object's owner must include the source owner. Enclose the source owner, sorry. There's the quote, which I'm not going to read because my time is running out, but you get diagrams like this. And well, I'm going to declare that that's a tree, even if it's not. But this is actually from the UPSA 98 paper. And the point here is that, we have a root and we have a safe, I guess we have a safe object here. And in order for the ICFP people in the room to feel comfortable, we've used a couple of pairs here rather than other things. So the point is, I guess, the safe object here owns these pairs. And what are you allowed or not allowed to do? Well, you're not allowed to do, for example, things like this, I guess. The dotted lines here are the ownership structures. So the root here isn't allowed to point to pair 2 because, well, why not? Presumably it's owned by this object, but this one here is owned. Why has he done that? This one here is owned by the root, so the root is allowed to have access to the second in the pair. You can't see, oh, bugger, all right, sorry, I didn't realize because it's behind me. So I guess the point is that these pairs can have references to their first and their seconds, and the dotted lines are ownership, so the left-hand pair is owned by that safe. The right-hand pair is owned by the root. The root is not able to get access straight through to the first pair, and this is what I realized. In spite of this paper being going on for 30 years old, it looks like there's a bug in the diagram. I should try and do the Donald Knuth thing and offer you a check that you promise not to cash, because I don't actually have very much money if you find a bug in a diagram in a paper that I've built my career on, and other people have built their careers and languages. Well, I claim that anyway. Whatever. Right. I'll have to look at the paper again. Or could somebody else please actually check the paper? Do you see the problem I'm saying? The problem is that there's an X on that link B, which says the root object should not be able to point to the pair, but I'm arguing if those dotted lines mean ownership, it can point to that pair. Because that pair 2 is owned by the root, but its pair 1 is owned by the safe. And so the root would not be allowed to have a pointer to pair 1, but it would be allowed to have a pointer to pair 2. I've even given this talk before and I didn't fucking notice. Sorry, it means I'm going to. Right, object ownership, here we go. Here's another paper. Again, I love the sort of low-res quality you get from going to the ACMDL and grabbing the bits. Again, what this means is given some owner, we can talk about stuff that is, or an object which is we're thinking of an owner of a group of objects, or the inside of it, I guess. It divides things into the inside and the outside. And again, the rule is you can't have any incoming pointers. No incoming references. Like I said, the target owner must enclose the source owner. And crucially, a thing that's different from, well, again, on the object-oriented side, it's not, I was going to say for ownership, for flexible alias protection, but in fact, some precursor systems like islands and like capsules and various other things also behave in this way, which is there's no restriction on aliasing inside. There's no restriction on aliasing inside. So that owner could be a link object that represents a whole, a list object that represents a whole linked list. And D, E, and F could be the elements of the list. The thing that then flexible language protection and ownership types extends that model with is the fact that F here can have a pointer to C. We can have outgoing references. So I can have a list, and I can keep the links in that list private, and I can alias them however they like, and then I can have links going out to other things, which is pretty cool. And you know, you can't necessarily do that easily in languages, some languages at least, whose names begin with R, and possibly some whose names begin with O, and, well, at least not yet, anyway. Did I mention I was looking for a job? Right. Sorry. All the things I tell my PhD students not to do, I'm doing. Then, you know, we started to think, and again, work here done by Tobias and various other people, I think. The question is, okay, we've got these heaps, we've got these kind of heap structures. What can we do with the stack? And this, in some ways, is where the ownership and the regions work, or the OO side and the functional side, are coming back together again, I think. We knew about region types in the ML kit when we were doing the first work on ownership types. There are a couple of big differences, and the main one was we kind of assumed we were always fully garbage collected most of the time, and that meant we didn't impose any region nesting, strong region nesting over the whole program in a way that, for example, the region calculus and the ML kit regions do. They're all very nested, whereas we were happy to say, well, we might have a garbage collector. So, you know, we might set up this deeply interlinked structure over here, and that might be interleaved through the execution of the program, and then that thing can go away, and it can go away irrespective of its temporal relationship with other regions that may have been created earlier and still be there, or may have been created afterwards and are still there. There's no global ordering. So, this is the next bit of the talk. Ownership, ownership, ownership. I've obviously moved things around. So, we're actually going sideways slightly. Here is another example. That's basically showing the same thing where I've drawn in purple links for the various ownership domains. You can see linked list, object. There's stuff inside the linked list, and then all of that might be contained in a wider context. Well, then what does this have to do with Rust, and what does this have to do with borrowing? Well, I wish I could skip this. Rust has this notion of copy and move semantics, and when I say Rust, I really mean it kind of comes from C++. I think it went from probably C++ to Rust and then back to C++ again. I can't remember the timing. C++ now also has, anyone know about C++ move semantics? That's kind of worrying. Don't tell the ICFP people because, well, don't tell the Rust people because they'd love to use a double ampersand if they could think of something for it. At some point I should write a paper called The Limits of Non-Alpha Numeric Characters in ASCII on Programming Language Design. How many different kind of things can we have when we express them with the syntax we've got in ASCII? So again, I'm just reusing slides, but I don't particularly want to. So Rust has this notion of a copy and a notion of a move. And it says in time that by default is move, which is actually a copy followed by possibly the compiler killing the source variable. Okay? And if you read the Rust book, it actually says the only difference between move semantics and copy semantics, which is why I really should have these slides around the other way, is whether you're allowed to access the source after the assignment. Under the hood, both a copy and a move can result in bits being copied in memory, where can means pretty much always will result in bits being copied in memory, although it might be optimized away. Okay, cheers. That slide was apparently so important that it's kind of there twice. Right, so now I really am slightly getting out of scope. I'm going to skip forward. What do we do about that? Well, yes, I am a serious computer scientist, really. I hope Brendan Eich didn't read this book before he designed JavaScript. I don't know that he did, but I don't know that he didn't. Anyway, this was a book done, again, about 25 years ago, talking about prototype-based programming languages. Self was just about to be kicked a touch or kicked in the head by Java, at which point almost all the Self group took what I call money from Sun Microsystems and then basically ported the ported the self hotspot VM to something called Java Hotspot. And then most of them have now retired independently wealthy, except Urs, who apparently lives on an island somewhere off the coast of New Zealand that he owns and basically does Google, yeah, runs the advertising. He doesn't run the advertising company. He just keeps the advertising company running. He's chief CTO or something. Anyway, sorry. So I just put up that because that is Dolly the sheep, and there is Dolly the sheep. Doesn't have that much, well, in some sense it does have a bit to do with prototype-based programming because one of the ideas behind self, and probably not the most important one, was, okay, we're going to make new objects not by appealing to a class, not by apostrophe, but by cloning, by getting an object and making a copy of it. And the problem with that is, if you know, and again, these terms are actually from Smalltalk, the problem is, well, how much do you copy? So if you make what's called a shallow clone, and most languages have this in, well, the catch is you probably won't copy enough. So if, in this case, I think that model's copying some kind of window, perhaps the red window, we're going to copy or making a green one, but it's sharing all the pre-existing resources that were already there. Things probably aren't going to work. On the other side, you can have a deep clone where, you can copy, sure, but you copy the entire world. How do you know where to stop? Well, you're going to copy the window, so you copy the window, and then you copy the window manager, and then you copy the underlying libraries, and then you just keep going. And I'm talking about it in kind of copying, but in fact, these problems arise in all kinds of areas where you actually want to do stuff with objects or with components or with whatever they are that are made up of other objects or components or whatever they are. Tobias gave a nice talk talking about possible Eka Python designs, or I think this is already there in JavaScript. If you're freezing an object to make it immutable so you don't have to copy it, you have the same problem. How do you know when to stop freezing? You might invite the little green men who are going to calcify your political system and agree that they can have Sevastopol, and then before you notice, well, we're in the Donbass, whatever, they just keep going, they keep going. How do you know when to stop? Well, cheap clone is basically a clone which says, we will use the ownership information we have in those kind of trees that I've been displaying, the ownership trees, to delimit these sort of things. So what we clone is we will clone, if we say clone a window, the thing in the middle, we'll clone all the components that we know belong to the window, but we stop. You can rent Sevastopol, but you can't leave the borders of the municipality because that's owned by somebody else. And in computer programs, that means, you can copy the window, and you will copy the window, and you'll copy all the resources that are specific to that window, assuming the ownership's been set up properly, but then you won't decide you have to copy the whole system. The reason I'm mentioning that is because the work I've been doing is looking at building models of Rust and Rust-like things and ownership-like things to think about and saying, okay, well, how do we handle putting Rust's move and copy semantics into this James's sort of object ownership world? And part of what I'm saying is, well, this is how we would copy move and this is how we would copy move semantics and copy semantics. Sorry, what I mean. Yeah, I mean move and copy semantics. Right, I'm going to go back. So the interesting question then is, okay, we actually now have two independent hierarchies at this point. We have the ownership hierarchy, which is, again, type systems that people in this room have been working, for rather a long time on. The linked list owning its links, being able to have references outside. And then, again, whether in the name ownership or just stack-based allocation or stacks, you also have this other structure, which are the method calls. So in this case, maybe you want to enroll a student in a course, and to do that, you're going to call an insert method on the table, and to do that, you're going to go down and call an add method on the linked list. Okay, now the catch is, given what I've talked about no incoming references, this is a fairly subtle point that most of the models of ownership types so far basically kind of wave their hands when it comes to the stack. There are probably a few that don't, but most of them say stack is kind of a bit special. Maybe we will look back and see which object was the receiver in the... Anyway. The problem is that, you know, fine, your enrollment method, if it's got an object that's owning something, it could have a pointer to the course, but then there's this no oncoming pointers rule. So how the hell do you get inside the course? So the answer is, again, work done by some talented students and postdocs and people, and less talented people. There are versions of this that have multiple ownership. And the idea here is, okay, I mean, probably this was done slightly after the peak of aspect orientation when, you know, having multiple dimensions of things or multiple aspects. I did hear people saying aspect in a tutorial on Sunday. And nobody in Uppsala land would have said that for 10 years. So it's nice to see it's coming back again. Multiple aspects here, you know, you can say, well, these their tasks are owned by workers, but they're also owned by projects, and maybe that controls who can modify what. And there's been type systems done to model that. What I'm hoping, what I think can be done, is we can combine these two ideas. So basically, when you call enroll, you can think of the stack frame as being inside the course object. The stack frame for the enroll method, and that now means that's got to have multiple owners, because if you think about it, it's got to be owned by its calling stack frame, and it's also got to be owned by or have access to the inside of, which is another meaning of owned by in these systems. It's got to have access to the inside of the table. And then the table calls insert on the list, which it can do. It's got a capability. It's got a pointer to the list object. It calls insert. To do that, it needs to make a stack frame for that insert. Where does that stack frame have to go? Well, it has to be inside the stack frame for the enrollment method, because the enrollment method might have created some temporary objects, and it's got to be able to get access to it, so it's still got to have that relationship. But it's also now got to be inside the table object. And similarly, the table object can ask the list to add an object, and then in order to run that, we make a stack frame inside the list, and we run the add method inside that frame, and that frame is both, it's got to be inside the list so that it can access to the links and stuff, and it's got to be inside the insert because there may be stuff there. Thank you. And I'm very nearly going to stop there, and it's kind of odd because the talk was called Against Borrowing. I've briefly talked about copy-move semantics, and I've talked about all those structures. And the slide I didn't get made was the one about borrowing. And in some ways, I'm going to say, do you know why? Well, obviously it's because, you know, I'm ADHD and various other things and didn't really have my time management under control. But also it's because if there is a borrowing, it's actually kind of like that link there. Okay, that outgoing reference. The outgoing reference from the link to, well, it says bucket, I don't know, I think it was a hash table of students and grades or whatever. So an outgoing reference, that's a reference which points to something older than you, points to something higher up on the stack. Okay? Those are what Rust calls borrows. You can't have a borrow that goes to an enclosing frame. You can't have a borrow that goes to something younger than you, right? The reason there are no slides is because I think borrowing is an epiphenomenon. Okay, I think borrowing is an epiphenomenon. I'm sorry if you... congratulations on the student, especially if you're in the room for doing a paper on the borrowing calculus. Congratulations, we do need that. We do need to understand precisely what on earth is going on at that really detailed level with the capability stuff. But remember the wood, the goblin wood, and remember that circle. Remember the goblin wood. If you take one thing away from this talk about why maybe thinking about borrowing is just kind of almost unnecessary. Borrows are references, and they are references that are bound by the ownership of the thing that you are pointing at, which is I can probably go right back to the slide, which is pretty much a quote from the 88 Uppsala ownership types paper. You know, so an object can point to something that is inside the target's owner. And that, I think, I'm going to claim is the forest. That is the big picture. And I wonder if thinking more about that big picture means we will be able to do more things in our languages than we can. I'm not saying the little pictures aren't important, and I'm not saying it's not important to actually be able to explain what's going on at a very detailed level of the operational semantics and the capabilities and the possibilities there for optimization and eliminating these things, especially if you're eliminating... But don't lose sight of the forest for the details of the trees. Thank you very much.
Right, we can take questions while the next speaker is setting up.
I've scared everybody away.
So I think I fundamentally disagree that we want to always look at the forest. I very often want to look just at the tree. And I see borrowing as a mechanism to focus on exactly a tree. Now we can think that the borrowing is a reference, but we can also forget that reference exists altogether. And with the move semantics, I can just have the tree, work on the tree, and put the tree back in the forest. So why should I always have to care about the forest? Why can't we design programs so that we do not have to care about forests?
Well, I think the answer is it's nice, nice work if you can get it. And you can probably get it if you try. But unfortunately, there are structures where we do need to think about invariance of wider enclosing contexts. There are times when we do need to look at the larger structures. And if you talk about doing the move, if you say you just move in and out, that is basically value result semantics for passing procedure arguments. And there's a nice but very obscure paper by Henry Baker. Read everything that he wrote in SIGCloud Notices, explaining why that's often not secure and will lead to differences in the semantics versus using references. I mean, in object-oriented terms, you might say, well, you lose object identity. Maybe you don't care, but you do. Jonathan.
Nice talk. I'm a fan of viewing the forest and have done it myself. At least tried to myself a few times. One of the concerns that I have is, what are we trying to get out of ownership in Rust, right? And I think the key answer that people tell me is we're trying to get safe manual memory management, safe concurrency. And so the question is, can we get that with the forest, right? How do we reconcile this desire for a big picture view, but also more flexibility, of course, in our programming, which is, I think, the point, and also get those properties?
At that point, I'm going to say, well, you really should listen to Sasha. I'll check that the person talking was actually, whose name was on the thing, which I could read. Sasha's talk about a verified thread-safe array in Rust, because I think you can. And I think, I should stop quoting Shakespeare. There are possibly more things in our philosophy of Horatio than we have thought of. One example would be, do you mind me mentioning cones? If you look at, for example, some of the stuff that Tobias and people are doing in Reggio, they are willing to have an object which is effectively an actor or a monitor for all its internal structures, right? And that's got some kind of lock on it, maybe a read-writer lock or maybe an exclusive lock. Once you do that, then again, on the concurrency side, the topology of the references inside that thing, inside that bit of the forest, is irrelevant to what happens outside. Maybe. Then you've got the issue of the outgoing references, but again, there are all sorts of options there. I'm not saying that you should necessarily just say, oh, well, we'll just go back to randomly writing pointers to everything and hoping. I'm not saying that. What I am saying is, I think that by improving, I don't even know if I want to say improving. I think there may be different trade-offs between conceptual models, between the way we think about our programs that underlie the languages we use to express our programs, that would be better places than the ones we're currently at, something like that.
Thanks.
That's all the time we have for questions.